we know that the acceleration vector now has a direction back toward the origin. And let's see, got an error there. That should be minus. Okay, so that vector is in the direction opposite the r vector. The question is, what's the magnitude of the acceleration vector? Magnitude of the acceleration vector is, well, the square root of the sum of the squares of its components, Pythagorean theorem. So we write the x component squared plus the y component squared, not bothering with the, well, we might as well have the negative sign in there. It's going to square out. And what does that simplify to? Now, this is a calculation you should have done many times already, especially if you're taking vector calculus and dynamics. If you square these things, you're going to get an expression out of which you can factor r squared omega to the fourth. You're going to get an r squared omega to the fourth here and here, so clearly you'll be able to factor those out. Now, they're within under the square root sign, so when you factor them out, they'll be under the square root sign, but then you can take the square root and you're going to get r omega squared. The rest of what you've got under here is just going to be cosine squared of omega t plus sine squared of omega t. I've written that down here, and that's equal to 1. So I guess I could insert here that equals a little trouble writing an omega over here, okay? So that equals r omega squared. But it should be clear, this is a standard calculation. It's a standard mathematical trick that you encounter again and again when you do these sorts of things. And you're going to need this to make sure you understand it. Okay. Then our conclusion is that the magnitude of A equals r omega squared, and that the A vector is toward the center of the circle. And that is opposite to the direction of r. Well, that's the reason it's toward the center of the circle. Its direction is opposite to that of r, therefore A is toward the center of the circle. So we're going to say that r omega squared is the centripetal acceleration of the point on the reference circle. And I could make that even more explicit. A equals r omega squared, and I'm going to put CENT down here to indicate that that's the centripetal acceleration. Now, question is, what is r omega squared in terms of v? V being the speed of the reference point, or the object moving around the circle. You should answer this question without looking at the answer, but here it is. V equals r omega. Okay, V, and that's something. Omega is the number of radians per second. If you multiply the number of radians by the radius, you get the arc distance. So this is arc distance per second, which is the speed. And then it follows, of course, that omega is v divided by r. Follows then that the centripetal acceleration, which is r omega squared, is, well, omega is v over r, so replacing omega by v over r, we get r times quantity v over r squared, and that's very easily simplified to v squared over r. Now, it was at this point that someone interjected that this is the normal component of the acceleration. And that's exactly right. It's exactly so for the motion that we're considering now, where omega is constant and r is constant. We have only the centripetal acceleration. We don't have a tangential acceleration. But we might want to go ahead and draw an arc of a circle here. And an r vector. V is tangent to the circle. But the acceleration vector, if V is constant, if the speed is constant on the circle, then the acceleration vector is back toward the origin. Doesn't matter whether V is constant or not. If the speed is V, then the centripetal acceleration is V squared over R. And that is perpendicular to V. So we call that normal. Normal to the velocity vector. The tangential acceleration that we would get if the object is speeding up or slowing down, let's assume it's speeding up, and I'll call that A parallel. The acceleration component parallel to V, that's going to be, well, our parallel components. We have a parallel component of acceleration and a perpendicular component or normal component of the acceleration relative to the direction of the vector V. In the videos I posted about a month ago, we have an analysis that gets into that. We have examples of motion on the circle that are accelerating, and we do talk about the normal and parallel components there. So I'm not going to talk about it here. It's not necessary for what we're doing right now, but it is something that I mention now because so many people at this stage of this course are doing similar things in dynamics and in vector calculus, or have done these things in vector calculus, so they're very relevant.